When we are finding a point in the plane using distance and direction, we are using what we call the polar coordinate system. The polar coordinate system consists of a fixed point, O, which is the pole. The pole is the same as the origin in rectangular coordinates. A point in a polar system is defined by an ordered pair, just like in rectangular coordinates, but instead of x comma y, we use the form r comma theta. If r is positive, then the point P is located r units in the direction of theta. If r is negative, then the point P is located r units opposite of theta. If r equals 0, then the point is at the pole. The coordinate system that I have showing on this page is the coordinate system we will be using to graph our polar coordinates. This center, this is O, which is the pole. And as you look, there are concentric circles wrapping around the pole. So this first one is a radius of 1. The next one is a radius of 2, and so on and so forth. Wrapped around the circle are the labels for the numbers on the unit circle, plus the pi over 12s, which we haven't had in the past. This is how you will find your angles. We first need to understand how to plot polar coordinates. So I have some examples to show you how to plot the points on a polar coordinate system. The first one is the point 2 pi over 4. What's a little different is that you find the angle measure first. So here's pi over 4. Notice that our r is positive. So when it's positive, you go to the second line out from the center on the line for pi over 4. So here's 1, here's 2. That is our point A. For B, we do the point of negative 4 pi. Here's our angle of pi. Now, our r is negative. When your r is negative, instead of going in the direction of pi, you go in the opposite direction. So we're going to move to the right along that same line. 1, 2, 3, here's the fourth mark. So this is point B. For point C, first of all, we want to do negative 3 pi over 4. So first remember that this is negative pi over 4. This is negative 2 pi over 4. Here's negative 3 pi over 4 over here. So now we know the angle that we're on. We want to go negative 6. So what that means is we're going to go backwards off of this. We're going to go across the pole, and we need to go 6. 1, 2, 3, 4, 5. The last circle before the last line before the end of the circle is 6. So there's our point C. For point D, we're going to do negative 5 pi over 3. So we're going to go in the downward direction all the way over here. This is negative 5 pi over 3. So this is the line we want. Because it's positive 3, we're going to go towards that angle measure, out towards the outside of the circle. Here's 1, 2, 3. So there's point D. In the rectangular system, each point is unique. In the polar system of graphing, there are an infinite number of ordered pairs that represent the same point on the plane. This is because we could do any number of rotations around the circle in either the positive or the negative direction and find another angle that lies at exactly the same point. This means that one way to find another representation for the same point is to add 2 pi to the angle measure any number of times to find the same point. On the other hand, if we start with the opposite of r and add pi any number of times, we would also be at the same point. If you want to find new representations for a pair of polar coordinates, you do one of the following. Use the same r and do your angle measure plus 2 pi or your angle measure minus 2 pi. Or you do the opposite of your original r and do your angle measure plus pi or your angle measure minus pi. In your homework in ALEKS, your directions are going to be to find 2 additional representations for the given point. Your answers must be negative 2 pi at the smallest and positive 2 pi at the largest. Our first example is the coordinates negative 5 pi over 4. We are just going to test each of our possibilities and see which one or ones will work. The r stays the same on our first ones. We take our original angle and add 2 pi. Now remember that if we have pi over 4 plus 2 pi, a common denominator for that would be 8 pi over 4. Pi over 4 plus 8 pi over 4 would give us negative 5 and 9 pi over 4. Our directions tell us that we cannot use any angles that are larger than positive 2 pi. 9 pi over 4 is too large, so we can't use that answer. It is still an angle at the same point, but because of our restrictions of 2 pi, we can't use the answer. Now let's do negative 5 and our original angle minus 2 pi. Pi over 4 minus 8 pi over 4 will give us negative 7 pi over 4. That is less than 2 pi, so this one is okay. To find the other possibilities, what we are going to do is switch our point to the opposite sign, so make it positive 5, and then do the original angle plus pi. Now remember, 1 pi would be the same thing as 4 pi over 4. This means that we would have 5 pi over 4 plus 4 pi over 4 is 5 pi over 4. 5 pi over 4 is less than 2 pi, so it's acceptable. Let's go ahead and look at the last possibility. Do the opposite of r, so we're going to do positive 5. We're going to do pi over 4 minus pi. This would give us 5. Pi over 4 minus 4 pi over 4 gives us negative 3 pi over 4, which is another answer that works. You can use any 2 of those 3. Our second example is the given point of negative 3, negative 4 pi over 3. We're going to start out by leaving the r the same and doing our original angle plus and minus 2 pi. Think of the 2 pi as being 6 pi over 3. This means that our new point would be -3, -4 pi over 3 plus 6 pi over 3 would be 2 pi over 3. That's less than 2 pi, so this point's good. Now let's try -3 and -4 pi over 3 minus 2 pi. -4 pi over 3 minus 6 pi over 3 would give us -10 pi over 3. That's more than 2 pi, so this point does not work. To try to find another one, now we switch the sign of r, so we're going to be doing +3, and then we also switch and do our original angle plus pi. Pi is equal to 3 pi over 3. So this point would be +3, -4 pi over 3, plus 3 pi over 3 would be -pi over 3. This is less than 2 pi as an angle measure, so we can keep that one. If we do +3, -4 pi over 3 minus pi, we would have 3, and then our angle would become -7 pi over 3. That's more than 2 pi, so we can't use that one. In this case, we only have two angles that do work. Our third example has the ordered pair of 5 pi. The process stays the same. Keep your r the same. Do pi plus 2 pi. Well, that's going to become the ordered pair of 5 and 3 pi. 3 pi is too big. We can only go 2 pi. So we're going to toss that one out. Keep r the same. Do your angle minus 2 pi. This would give us 5 and -pi. That's okay. It's less than 2 pi, so we're going to keep that one. Now, switch the r, make it -5, do pi plus pi. This would give us -5 and 2 pi. Our directions had brackets around the -2 pi and the +2 pi, which means that those answers are both included, so this 2 pi is allowed. That would be an acceptable answer. Just to show you what the third possibility is, we would have -5, and then we would do pi minus pi, which gives us -5 and 0, and this too is acceptable. We're going to use this figure to help us find a couple of equations that we are going to need to use for the rest of this module. If you look at this figure and go back to what we have previously learned, we know that the distance across the horizontal axis is x, and the distance up to the point that we have there is y. And we have a right triangle created there. So in relationship to angle theta, using our old, already known definitions, we could say that the cosine of theta equals adjacent over hypotenuse, which would be x over r. we could say that the sine of theta is opposite over hypotenuse, so we would have y over r. We're going to solve these two little equations for x and for y. On the cosine equation, if we multiply both sides by r, we now wind up with an equation that says x equals r cosine of theta. Doing exactly the same thing on the sine equation, we would wind up with y equals r sine of theta. These come directly from how we defined sine and cosine. We are going to use these equations to help us convert between polar and rectangular coordinates. Our first point that we're going to convert is 4 and 3 pi over 2. Remember that when you have polar coordinates, the first number is always your r, the second number is always your theta. We said just before this that x equals r cosine of theta and that y equals r sine of theta. Those equations tell us exactly how to find x and y. So x equals, our r is 4, cosine our theta is 3 pi over 2. So we're going to look at our unit circle and see that the cosine of 3 pi over 2 is 0. So we have 4 times 0, which is 0. We now know that our x-coordinate is 0. Our y-coordinate is 4 times the sine of 3 pi over 2. So it's 4 times unit circle again, sine of 3 pi over 2 is negative 1. So our y-coordinate is negative 4. This means that the rectangular coordinates for that point would be 0, negative 4. On B, our point that we are converting is 3, negative 5 pi over 6. Our formula tells us that x equals the r, which is 3, times the cosine of theta, which is negative 5 pi over 6. If you go to the unit circle and replace cosine of negative 5 pi over 6 with what it's equal to, you will find negative square root of 3 over 2. 3 times negative square root of 3 over 2 is negative 3 square root of 3 over 2 by multiplying those fractions. The y-coordinate is the r times the sine of negative 5 pi over 6. So this will become 3 times negative 1/2, which is negative 3/2. This makes the rectangular version of our point negative 3 square root of 3 over 2 and negative 3/2. For the polar coordinates negative 6 and 4 pi over 3. To find x, we're going to do r negative 6 times the cosine of theta 4 pi over 3. So we're going to have negative 6. Cosine of 4 pi over 3 from the unit circle is negative 1/2. Negative 6 times negative 1/2 is 3. The y-coordinate will be r of negative 6 times the sine of 4 pi over 3. So we will be doing negative 6 times negative square root of 3 over 2. This simplifies to become positive 3 square root of 3. So the rectangular coordinates for this point are 3 and 3 square root of 3. To convert from rectangular coordinates to polar coordinates, we have two equations that we're going to use. The first is that r equals the square root of x squared plus y squared, which comes from doing the Pythagorean theorem on the figure we had before the last example. And using the definition of the tangent, we know that the tangent of theta equals y over x. So an angle theta has to equal the inverse tangent of y over x. The steps you're going to follow to solve these problems: find in which quadrant your original point falls. Then you're going to find r using our given formula, and then find the angle using the inverse tangent. Our first example of converting rectangular coordinates to polar coordinates is the rectangular point of 4, -4. If you think about that, this point you would go right 4, down 4, so this point falls in quadrant 4. Now we're going to find r by doing the square root of our x, which is 4, squared, plus our y, which is -4, squared. Well, this gives us the square root of 16 plus 16, which is the square root of 32, which simplifies to be 4 square root of 2. Our theta will be the inverse tangent of the y, -4, over the x, which is +4. Well, that gives us the inverse tangent of -1. So ask yourself, what angle in quadrant 4 has a tangent value, a y over x, that would equal -1? That angle would be at -π/4. So our polar coordinates would be our r that we found, 4 square root of 2, and our theta that we found, -π/4. Now we want to find the polar coordinates for the point of -1 square root of 3. First of all, recognize that this point, if we go left 1 and up 3, puts us in quadrant 2. Now we're going to find r. We're going to do the square root of x squared plus y, which is the square root of 3, squared. So we're going to have the square root of 1 plus 3, which is the square root of 4, which is 2. Now to find theta, we are going to do the inverse tangent of our y, which was the square root of 3, over our x, which was -1, and then look at the unit circle in quadrant 2. If we put the y over the x, where do we get a square root of 3 over -1? That happens at 2π/3. Our polar coordinates then are 2π/3. In the last example, the angles that we found were actually special numbers on the unit circle. When the angles are not on the unit circle, we have to do something a little bit different. We still find r, and we still use the tangent, and we use the calculator to find the inverse tangent. What you have to remember is that when we use the calculator to find inverse tangent, the answer that we get is quadrant 1 if it's positive, and quadrant 4 if it's negative. This means that if our original point is in quadrant 1 or quadrant 4, then the calculator answer is our angle measure. We're done. However, if the angle is in quadrant 2 or quadrant 3, we have to add 180 degrees to the answer. We do this because quadrant 2 is 180 degrees from quadrant 4, and quadrant 3 is 180 degrees from quadrant 1. If you want to find polar coordinates for non-special angles, if the point is on the x-axis or y-axis, just find the coordinates by looking at the graph. If the point is in quadrant 1 or quadrant 4, use the r equals formula and theta equals tangent inverse of y over x. If it's in quadrants 2 or 3, use the r equals formula and theta equals tangent inverse of y over x plus 180. On the problems in ALEKS where you are converting polar coordinates to rectangular coordinates and they are not special angles, you are always going to round your answer to the nearest hundredth. Our first example is the rectangular point of 2, -5. First of all, let's think about where this falls. If we go right 2 down 5, we are in quadrant 4. This means we're just going to use our two formulas and our calculator, and the answers that we get will be our answer. So r is the square root of x squared plus y squared. 4 plus 25 gives us the square root of 29. This means that our r comes out to be 5.385, and then that would keep going. Theta is the tangent inverse of the y, -5, over the x, which is 2. If you do this on your calculator, you get -68.1986. Make sure that you're in degrees on your calculator when you are figuring this. This means then that our point is 5.39 because we're rounding to 2 decimal places, and -68. Now, because this third place is an 8, we have to round up the second place, which then rounds up the first place, so it'll become 0.20. For the point -3, -4, to plot that, we would go left 3, down 4, which means we are in quadrant 3. As soon as I see that I'm in quadrant 3, that needs to be like a neon sign reminding me I need to do the plus 180 when I find my theta. R will equal the square root of -3 squared plus -4 squared, which will be the square root of 9 plus 16, which is the square root of 25, which is 5. Theta will be the inverse tangent of our y, -4, over our x, -3, or the inverse tangent of positive 4/3. And don't forget, we have to do the plus 180 on this. If you do this on your calculator, you will get 233.1301, making our polar coordinates 5, 233.13. Do a quick check and make sure, is the angle 233.13 degrees going to fall in quadrant 3? And yes, it does. To convert the point -5, 1, first let's recognize if we go left 5, up 1, we are in quadrant 2, which means we need to do a plus 180. Let's find r. It's going to be the square root of -5 squared plus 1 squared, which is going to be the square root of 25 plus 1, the square root of 26, which is 5.0990 from your calculator. Inverse tangent for this problem. Y is 1, x is -5. Don't forget to do your plus 180. Doing this on the calculator, you should get 168.6901. Think about that. Is that in quadrant 2? Yep. So our point then is 5.10 because we have to round to 2 places, and 168.69 for the theta.